Hello, my name's Karl Wegmann, and I, along with my co-author Corey Scheip, are excited to talk with you today about a new Google Earth Engine application called HazMapper that we've created. First, I want to introduce the HazMapper, and then we'll use it to look at Coseismic landsliding from the magnitude 7.8 2016 Kaikōura, New Zealand earthquake. So first, what is HazMapper? HazMapper is a Google Earth Engine application, as I mentioned. It's open access, an open access application for natural hazard mapping. So it started out with our desire to improve mapping and assessment of storm-induced landslides along the Blue Ridge Escarpment of Western North Carolina. And I'll highlight an event that happened in May of 2018 when this portion of Western North Carolina received heavy amounts of precipitation that caused dozens of rainfall-triggered landslides and debris flows off of the Blue Ridge Escarpment, in this case along the margins of the valley walls of the Pacolet River. So here's one aerial image showing the initiation and debris flow tracks coming down here, and a house down here on the debris fan where there was unfortunately a fatality. So one of the things we wanted to do when working in these types of environments is to see if we can remotely sense or remotely identify these types of mass wasting features. And so we turned to the normalized difference vegetation index to identify potential areas of mass wasting in these heavily forested environments. And the basic concept between the NDVI metric is that in the near infrared, healthy vegetation has a very high reflectance value versus the reflectance value returned in the visible red portion of this spectrum, and whereas unhealthy vegetation or soil or rock has a much lower spectral reflectance in the near infrared. So the NDVI equals the near infrared minus the visible red divided by the near infrared plus the red. And so this is what that would look like. So initially we're processing single satellite images to derive an NDVI raster in the GIS environment. So here's a pre-event NDVI image with high NDVI values, except for the bare bedrock cliffs. And then the post-event image in yellow are the outlines of the mapped landslides from the North Carolina Geological Survey, showing that in fact we can, for the most part, track the location of where these debris flows, landslides and debris flows happened using Sentinel-2 10-meter pixel satellite images. Here would be kind of the resulting NDVI difference raster. So we download the data to our PC, we do local processing with ArcGIS and Python, at least initially, and then we were calculating individual pre-post difference rasters. And this was fairly time and computationally intensive. So we realized that there's definitely promise in this method in this type of environment, but that we needed some way to be able to search bigger areas more quickly and more efficiently. And so we turned to Google Earth Engine, and this is where we developed this application called HazMapper, which is a tool for the detection of landslides or vegetation disturbance anywhere on Earth, using free data, open source methods, and requiring only an internet browser to execute. So Google Earth Engine is currently free for research, nonprofit, and educational use. The data is hosted by Google and the processing happens on their remote servers. The code, which you can see the upper part of the code window, the code is written in JavaScript. The code for HazMapper is open source and available for non-commercial purposes. Currently in HazMapper, we have the ability to identify surface detection changes using Landsat 7, 8, and Sentinel-2 satellite platforms. So this gives us 21 years of multispectral imagery available in HazMapper at either 30 or 10-meter pixel resolution. Currently, there's no commercial higher resolution satellite imagery available in Google Earth Engine or therefore in HazMapper. This is what the Google Earth, the HazMapper web-based user interface looks like. There's a parameters window where the user inputs some variables, which I'll talk about in a minute. You have the ability to toggle on and off different layers and to change their transparencies. You have the ability to download data as tag geotiff image files. You have the ability to click anywhere on the map and return the pixel value for that location. You have the ability to digitize, heads-up digitizing within the HazMapper environment, and then export those digitized lines, points, or polygons to Google Earth or a GIS platform. And we have we have some curated examples to help get folks started. So the event parameters window, this is where everything starts. So and this window is set up for the earthquake in New Zealand, which happened on November 14th, 2016. So we're going to choose a pre-event window of 1.5 months, a post-event window of half a month. We can modify filtering out cloudy images. So we set a threshold for the maximum cloud cover percent, and then a slope threshold to exclude low slope areas from the analysis, oceans, lakes, rivers, and gently sloping land. So HazMapper utilizes multi-temporal stacking. So it capitalizes on the technique within Google Earth Engine to perform pixel-wise calculations for the generation of a greenest pixel mosaic image from the user-defined pre and post-event image stacks. So this greenest pixel mosaic is a single composite image generated from all images that record the pixel with the highest NDVI result, or the greenest pixel. And the output from HazMapper is what's called the rdNDVI, or the relative difference NDVI raster. So HazMapper outputs a relative difference NDVI values following the approach of Ambrose et al. So the relative difference NDVI is the NDVI of the post minus the NDVI of the pre greenest pixel composites images divided by the NDVI of the pre plus the NDVI of the post, and the square root of that multiplied by 100 to get it into percent format. So the results illustrate areas of the landscape that have either gained or lost vegetation, so either an increase in NDVI or a decrease in NDVI pixel values across the event is constrained by the pre and post event window date range. For visualization purposes, HazMapper applies a color scale within the domain of -50 to +50% rdNDVI change. And here's an example of a debris flow that happened in April of this year in Western North Carolina, where you can see the obvious removal of vegetation here in the photograph and the corresponding HazMapper rdNDVI result here on the left, with values again ranging from greater than -50% change to positive 50% change. So where vegetation increased a little bit, the trees were regreening here. Along the track here, the vegetation was completely removed. So the advantages to HazMapper: it runs in a web browser, no specialized software is needed, it's global in scope, and it iteratively updates as you move around spatially within kind of the Google Map environment. Analysis happens in seconds. There's no need to download large data sets, and it outputs and save results as geotiffs for further processing and analysis in your preferred GIS platform if you choose. The limitations: it's limited to areas with vegetation, right? Because we're using vegetation metrics, the NDVI. So it doesn't work for areas characterized by standing water, snow, ice, bare rock, and soil. Such are often found at high elevations or latitudes. So that is an obvious limitation. Clouds and smoke may result in large decreases in returned rdNDVI values unrelated to ground surface vegetation change. So that's something to be cautious of. And the current release is not a semi-automatic landslide mapping application, but we are working on that. And so that brings me to the New Zealand example, where in 2016, there was this very large earthquake in the northeast portion of the South Island of New Zealand. Following that event, Massey and colleagues mapped more than 10,000 coseismic landslides across an area of about 10,000 square kilometers from aerial and satellite imagery. So here's the location on the inset map. The red lines show the surface rupture of that 2018 event. The pink and green circles are the mapped landslides from aerial photograph and satellite imagery. And so we're going to use a portion of this inventory as training data to seed a random forest model for landslide detection within the HazMapper Google Earth Engine environment. Here again, here's our model setup. Here in yellow are the polygons from the Massey et al. 2018 inventory. From this inventory of over 10,000 landslides, we randomly selected 100 landslide polygons as training data, and then we created an additional 150 not landslide polygons. And so those were input into the random forest model as our training data. And our predictor variables for either landslide or not landslide included slope, rdNDVI from HazMapper, pre-event NDVI, 10 of 13 Sentinel, and 10 of the 13 Sentinel-2 bands that are included in the Google Earth Engine library of the Sentinel-2 data. We use a random forest model with 200 decision trees that are being operated on every 10-meter pixel within the data set, and this results in a binary classification at greater than 50% confidence that it is a landslide, that's assigned to 1, less than 50% confidence that it's not I messed that up, less than 50% confidence that it's a landslide, or it's not a landslide, that'd be assigned to 0. So on the left, here's our post-event satellite image, and you can see for a portion of the study area, you can see Coseismic landslides in this satellite image. If I turn HazMapper on, the warm color, the bright areas are areas where we, using the rdNDVI metric, would suggest that there was vegetation change likely resulting from landsliding. And then here we'll get to the random forest model output in just a minute. So here's the original inventory from Massey et al. In 2018. Here's the HazMapper, the base HazMapper rdNDVI result. And then when we include all the different parameters into the random forest model, and returns out gray areas are it is a landslide, and green areas would be classified as not landslide. And I think we do pretty well for a first pass. Here now in yellow, I've overlaid the landslide inventory. So for most of the large landslides that they have in their inventory, we capture those. There are some places, for example, down here, that we predict that that's a landslide given input variables, but they don't have in their inventory, and we don't show as areas of rdNDVI loss or vegetation loss. And there are other areas where we would predict that there's a landslide. The HazMapper identifies these as areas of rdNDVI associated with landsliding, but they're not in the inventory. So this is something we're working on. This is a work in progress, but our goal is to get a fairly robust random forest model working within the HazMapper Google Earth Engine application that will be available in open access for everyone. So in conclusion, HazMapper is an open access multi-hazard mapping application developed and run in Google Earth Engine that only requires access to the internet and a browser. All computation is performed on remote Google servers. HazMapper utilizes the rdNDVI metric to highlight changes in surface vegetation before and after landslides or other natural or anthropogenic events. Currently, we're working to integrate machine learning into future updates to the HazMapper Java code to allow random forest binary classification for landslide events. If you have a well-curated landslide inventory and you would like to collaborate with us on this effort, please send us an email. Thank you, and hope you enjoy the rest of your GSA meeting.